Thank you. It's good to be here, at least virtually. Wow, it looks like a very big audience there. I'm presenting my screen. Can you see it?
Yeah, we see your presentation.
Okay, excellent. This is me. I won't talk too much about me, but I'm the technical education lead here at Web3 Foundation in Zug, Switzerland. And today I'm going to discuss the basic architecture of Polkadot and its interoperability using parachains, as well as the particular protocol that we're using to communicate between them. Now, this is obviously going to be very high level, but I will also show some examples of this in actually occurring, us doing some cross-chain communication. And there is a video from Robonomics that I believe also you have and can display after I talk, showing how XCMP works. So first, I want to, what's probably going to be a little bit, hopefully not too boring, but a little bit foundational, simply because I want to really make sure you understand how Polkadot uses some of the basic concepts of blockchain to provide scalability and interoperability. So please just bear with me, even though it may seem very simple at first. So if we think of a basic blockchain, right, we can think of this as a bunch of blocks, obviously, and in each block, something happens that changes the state of that blockchain. So here we have some Bitcoin, and every block changes the state. So if Alice gives 1 Bitcoin to Bob, the state of the blockchain in that block changes from Alice having 97 Bitcoins or whatever it means to 1 fewer, and Bob gets 1 more. So we also have some rules in this blockchain. So these transitions from one state to another can't just be anything, right? We know that if Bob has 1 Bitcoin, he cannot give 100 Bitcoin to Sue, since he only has 1 in his account. So there are, when we talk about how we're working here, there's a couple of terms that I want to make sure we understand. That the state of the blockchain is simply what's circled here, that there certain accounts have certain amounts. Obviously, other blockchains, you think of Ethereum or any smart contract chain, is going to have more complicated state, but it's still a state of being. There's a state transition caused by a block that changes the state of the system. And there is a state transition function. So what are the rules for these state transitions? Now, obviously, these can be very simple, like in Bitcoin, or they can be more complex, like in Ethereum or other chains. But if we think of a blockchain as simply some beginning state, a state transition function, and then state transitions based on input, how does the state change? We can look at this in a more abstract way. What is a blockchain? So we took this idea at Polkadot and said, well, there are some parts of developing a blockchain that aren't really essential to the rules of that blockchain. Like how do we connect and find other nodes? What sort of codec should we use when we're transferring data over the network? Connections for RPC, right? None of this is really relevant to the rules of the blockchain itself. It's just extra work that had to be done if you want to make a blockchain. So what Parity did was develop this tool called Substrate that lets you make a blockchain, and you get many of the features built in, right? So many of these ancillary features, like transmitting transactions and developing a consensus and civil resistance mechanisms built in, And then as a developer, you can focus on developing a blockchain that has the particular rules that you want, called the runtime. So this is just that state transition function that we discussed earlier. Do you want to have smart contracts in your blockchain? Do you want to have a particular type of governance? Do you want to have the ability to have proxies? Do you want privacy? All of these things are part of the runtime as opposed to really the running of the nodes. So if you take this together, right, where individuals can build their own blockchains, one thing they don't want to have to worry about then is the security of the network. And so one way to share security is the architecture we have, where there's a central relay chain. If you're familiar with ETH2, this is very similar to the beacon chain, and parallel chains or parachains that connect to the relay chain and share security with it. So we can have these individual blockchains that have their own rules, and some of these blockchains may, what we call, bridge out to external blockchains like Bitcoin and Ethereum, and also communicate and interact with each other. So if we look at the structure of these nodes, we have something called the Polkadot host, which again is relatively similar, if not exactly the same, amongst all of these nodes, parachains and relay chains. And we have a state transition function. So the rules of this blockchain, what features it has, what is considered a valid transaction, invalid transaction, etc., written in WebAssembly. So right now we have tools for building that with Rust, but any language that compiles down to WebAssembly can be used. And if you are running a parachain, you define your rules, and when you connect to the relay chain, you basically tell the relay chain, here are the rules that I promise to live by, right? That any state transition on my parachain has to meet the rules that I defined when I first started. And inside of this WebAssembly can even be the rules for how to change the rules. So you can have something where the network is upgraded, additional features are added, etc. And we actually see this quite often in the relay chain and in some of the early parachain candidates, where there are runtime upgrades without a hard fork. We just push out new approved WebAssembly. People that are holders of the token can vote that they do want this upgrade and actually can update the rules of the blockchain to add new features or remove features even. We've done that in the past. Or add new rules to the chain. And this happens automatically. There's no need for the host to update, right? Because we're just sending out this new WebAssembly actually over the chain. So I'm going to skim over a lot of the complicated details here because we could really get into this very deeply. But if you look at the right of the screen here, this is the relay chain. And remember, when this green parachain decided that it wanted to join the network, it gave a copy of its WebAssembly code, its state transition function, how it was going to change state from one block to another, and what are the rules. And then every time a new block is generated by this parachain, special nodes called collators will send a proof of validity. So this is a proof that there was a valid state transition by the parachain. And there actually is a bit of interaction between the relay chain and that individual parachain to make sure that the parachain is following that it gave to the relay and prove that this state transition occurred. So not all of the parachain nodes have to connect directly to the relay chain. This is part of scaling, that we don't need to have everyone connected to the same network. We have these heterogeneous shards that have some connections, right, to the relay chain. Not every single node has to connect to the relay chain. And actually, as long as one honest node connects to the relay chain, they can continue to produce blocks. So you can have your own chain that may have hundreds of nodes running on it, but as long as one of those is interacting with the relay chain and is honest, then you are, even if there are many other dishonest collator nodes, then you can be guaranteed that there are valid state transitions occurring here. So the question then becomes, so how does this help us, right? Why is this interesting? Well, we saw that it allows people to make their own blockchains, and we see in our growing ecosystem that there are some things that you can't just do with a smart contract. So, for instance, Alla, it allows you to make privacy-protected smart contracts, where the smart contract execution is actually privacy-protected amongst to a certain group. We have Akala, which does DeFi and allows like Oracle transactions to have special precedence, which is again something you can't really do at the smart contract level, and so we see a lot of potential attacks because of that. And what makes this even more interesting, besides the ability to create specific blockchains for a specific purpose, is that we can still have interactions between these blockchains. So it allows these heterogeneous chains, these chains that have very different capabilities, but they share some similar concepts. They share the ability to share security and to communicate with each other, because they're all based on this idea of this abstract virtual machine running WebAssembly and a particular API for how they will interact with each other. And since they're sharing security, the interactions actually there are some differences, but they're very similar to the way that you can compose complicated DeFi interactions on Ethereum or other smart contract single chain. But they're happening in a scalable way and in a heterogeneous way. So we do this through a technology called XCMP. So we have all of these chains running. They're sharing security, and we know that they are following the state transition functions that they signed up with. But they are going to want to interact with each other. So we have this tool called cross-chain messaging protocol that allows for that. We actually right now have on-chain only something called XCMP Lite, but that is the fallback for XCMP when it doesn't work. So I'll just walk through XCMP and then I'll walk through XCMP Lite and then XCMP, but just know that the full XCMP does not yet work. But that is something that we can upgrade to forklessly, again, just by updating that state transition function, that WASM runtime. So here we have two parachains, on the left, the green, and on the right, red. And green wants to trigger a contract A that is on the red parachain. So what we can do here, this is XCMP Lite. So again, there will be some improvements to this coming in the future. On the relay chain, a channel is open that has an outbound queue from the green parachain and an inbound queue from the red parachain. So we know We then are going to send this message, so basically an encoded version of the message to call contract A with whatever parameters from whatever account. And it will get put in the outbound queue from green and also in the inbound queue for red. And this is part of the relay chain state transition function. So the relay chain has this as part of its runtime. And since all of the parachains are following the relay chain for in terms of finality, we know that as long as blocks are being produced, that this message will end up at red parachain. So we actually can prove that it will go into the outbound queue and the outbound queue of green, the inbound queue of red, and then leave the outbound queue of green and leave the inbound queue of red and actually end up on the red parachain. So as long as blocks are being produced, as long as the parachains are staying connected with the relay chain, then we actually can verify that these messages are going through. There's actually also a technology called SPREE, Shared Protection Runtime Enclave Environment, execution enclave, that will also allow the green parachain to know how the red parachain will interpret that message. So it's not as though it's just an arbitrary sequence of bytes. You can verify that since you have access to the state transition functions of all of these parachains that you're sending to, you actually can verify that, oh, this sequence of bytes actually does mean this. This is the effect that it will have. So this is the basic version of XCMP. The problem with this, of course, is that the relay chain becomes a bottleneck if we're putting all of these messages onto the relay chain. We're looking to have approximately 100 parachains that are producing blocks every 6 to 12 seconds. So you can imagine that this would, after a while, be a big bottleneck. So we know that it's something we need to work on. And so this is the full version of XCMP. I just want to show it to you first from a node perspective instead of a block perspective here, where gray is the relay chain, and we have our green parachain and red parachain. And we have certain, collators that instead of talking to the relay chain, instead of connecting to the relay chain, they will actually be full nodes of 2 different parachains, and thus can send messages directly from one to another. So the green parachain will just put a hash of the message and let the relay chain know that it did send a message to the red parachain. And the red parachain can will know that it should expect this message and actually can verify that it received it with the relay chain. So obviously this is a very simple example. We can use a sort of gossip protocol or a flood protocol to get this spread from one message to another, one parachain to another. And if there is a problem with this, that it can't find a path to it, or a node goes down or is malicious, then we can fall back to the HRMP or XCMP Lite version of putting the message actually on the relay chain. But that's sort of a suboptimal way of doing it. So if we look at this from a chain perspective and not a node perspective, obviously there may be more blocks in between, but just for ease of understanding, I put just a few blocks on this. Green sends a message to trigger contract A on the red parachain, and it sends a hash to the relay chain, and it goes into the queue. So our queues are now just storing hashes. They're not storing messages. So this is going to be much more efficient, since hashes are fixed size digests. And when the red relay chain gets this message externally through the nodes, then it can verify that with the relay chain, and it issues a hash that yes, it received this message, and lets the relay chain know that it did in fact receive it, and then it triggers the contract. So that's this in theory. I always think it's fun to see this stuff in real life. So I'm going to, if you just give me one moment here to connect, I'm going to go and show you some of this operating on a testnet. But this is in fact available on Kusama. So this is the Parachain, excuse me, our Canary network, where we put code before putting it onto Polkadot. So this capability is not on Polkadot, but it is on Kusama. So let me go to West End, which is our testnet. And what I'm going to do teleport, that is transfer some funds from one chain to another. So if I look at my accounts, I can see my West End Bill 2 here has 376 Westies, our testnet tokens, WNDs. And I'm going to move them over to West Mint. So West Mint is our other network. So I have 376 on West End. West Mint is a parachain, so you can think of it as one of those green or red chains here. You can see on this chain, my same account has 104 Westies. So let me go back to West End, and I'm going to send a message that proves that I reduced my number of Westies on this account, and I would like, and thus I can increase them by that same amount on the parachain. So I will send 5 over from here. So I'm going to send from West End Bill 2 to the same address, but on a different chain. I could send this to a different address if I wanted to, but just to make it easy. And I'm going to send 5. Some transfer fees will be taken away from that. And now we're going to teleport and sign and submit. So my transaction is now being broadcast and then sent to, there we go. So it's sending, you can see XCM palette. So it's doing cross-chain messaging. But actually it was very fast. It usually takes about 12 seconds or so, but I guess I got lucky. We can see I'm now down to 371 Westies. But on this separate parachain, Westmint, so a different chain entirely, I have now increased from 104 to 109 Westies. And the reason we can do this is because all of these chains are working in the same web of trust, right? So even though they are separate chains, they can trust, because they all trust the relay chain, they all can trust that this actually happened. I did, in fact, reduce my account balance by 5 here, so it is safe to increase it by 5 on the parachain. So this, again, is a really high-level overview of Parachains and XCMP. Robonomics also put together a video of this with a little bit more detail for their particular parachain and for their more specific use case. I'm sorry, I don't know. Do you want me to play the video, or do you have that on your end that you can play?
Yeah, Bill will do it on our own. Do you hear us?
I'm sorry, it's really fuzzy. I have trouble understanding.
Yeah, I just wanted to tell you that's very amazing presentation. Thanks a lot for your intro into the Polkadot.
I'm sorry, I can't understand you. Can you type in the Telegram or something? If you could,
Yeah,
I
sure,
can't understand.
sure, yeah, sure. Спасибо большое, Биллу. Я бы хотел пригласить Сергея.